This is part 2 of quantum chemistry. Now we will extend our discussion to multi-electron system. So what we basically want to apply Schrodinger equation to multi-electron system, because we know from hydrogen atom problem that the system with one electron is exactly solvable. So hydrogen atom or hydrogen-like system, hydrogen atom or hydrogen-like systems like helium plus, lithium 2 plus, all are one electron system. So these systems, one electron systems are exactly solvable. But what about the other systems which has more than one electron? The simplest example is helium atom. So if we want to extend Schrodinger equation to helium atom, then what will be the result and how one can solve the helium atom system to get the required energy. Now before going to solve the Schrodinger equation for multi-electron system, it is required to write the appropriate Hamiltonian for the system. Now we know this is our Schrodinger equation, A psi is equal to E psi. So for multi-electron system we have to first write the Hamiltonian and the wave function. So there are two parts. One is writing the Hamiltonian properly, and another part that involves the choosing of the wave functions. We will come to the wave function parts later of our lecture, but here we will emphasize how to write the proper Hamiltonian of a multi-electron system. Let's start with helium atom. So helium atom, this is basically one nucleus, two electron system. One nucleus, two electron system. So we can draw the pictures like this is helium nucleus, and these are two electron. This is electron 1, this is electron 2, and this electron, this is R1 from the nucleus, this is R2 from the nucleus, and the inter-electronic distance, let it be R12. And this nucleus has a mass m. It has mass m, capital M, and charge, we know this is charge is plus JD, and for helium this is plus 2 electron. And these two electrons are same, and they have the electronic mass Me. Now we have to write the Hamiltonian of this system. So for this system, there are kinetic energy of the nucleus and kinetic energy of the electron also, and there are potential energy terms for the nucleus and the electron 1 interaction and nucleus electron 2 interaction, and there is another term that is inter-electronic repulsion term between the electron 1 and electron 2. So how one can write the total Hamiltonian of this system? So let's try. So total Hamiltonian of the system can be written is, first of all we have to write the kinetic energy part, and then we write the potential energy part. Kinetic energy part involves the kinetic energy of the nucleus, and the kinetic energy of the electron. So for kinetic energy of the nucleus, we can write it minus h cross square by 2m del n square. This is Laplacian operator and it involves the coordinate of the nucleus. Now we write the kinetic energy part of the electron 1 and the electron 2. You will give minus h cross square by 2me. This is the mass of the electron, and this is Laplacian operator for the electron 1, and minus h cross square by is actually 2me del 2 square. This is the Laplacian operator for the electron number as 2. So this is the kinetic energy part. There are also potential energy part. So plus the potential energy part. There is in nucleus electron attractive Coulomb potential. So this is attractive, and we know that attractive Coulomb potential is written as minus. So it is minus electron charge and nuclear charge. So it involves minus 2 square. 2 is the nuclear charge and E is the electronic charge. So it gives minus 2 square by 4 pi epsilon 0 R1. This is for the electron 1. This is the potential energy for interaction between nucleus and the electron 1. And now we write nucleus interaction between the nucleus and the electron 2 is also attractive in nature. So it also gives 2 square by 4 pi epsilon 0 R2. And there will be another term, that means potential energy of interaction between the two electrons, and it is, as it is repulsive in nature, so the sign will be positive. Only attractive potential are signed as negative. So here is interelectronic repulsive term, so we will write it as positive terms. Positive Coulomb potentials, that will be E1 E into E, that will be square by 4 pi epsilon 0, and the distance is R12. Okay, so this is the total Hamiltonian for the helium atom system. Now we already know that Born-Oppenheimer approximation is a very good approximation for atomic and molecular system, and it says that the kinetic energy operator, that means this part, the kinetic energy operator of the nucleus, here the mass of the nucleus arises in the denominator. So as the mass of the nucleus is very high, so this term is negligible. We already know Born-Oppenheimer approximation says that during electronic transition, nucleus remains as fixed. So after Born-Oppenheimer approximation, the equation of the Hamiltonian will be simplified a little bit. We can write it as H operator. This part will be negligible. We can neglect this part. Nuclear kinetic energy part can be neglected because the mass of the nucleus is so high. So this part will be not be there, and the rest part will be the kinetic energy and the potential energy part will be there. Apart from the first part, all other parts will be there. So this is the total Hamiltonian after Born-Oppenheimer approximation. So we will take it as the Hamiltonian of the system. Now if you will take the Hamiltonian, which takes the forms like H operator is basically now minus H cross square by 2me del 1 square plus del 2 square. This is the two kinetic energy part of the electrons, and there is the potential energy part. And this potential energy part, we have already written that is minus 2 square by 4 pi epsilon 0 r1 minus 2 square 4 pi epsilon 0 r2 plus square by 4 pi epsilon 0 r12. This term is the interelectronic repulsion term. Interelectronic repulsion term. Suppose this term is not there, then basically this is a separate two hydrogen atom system. What I am calling is that if this term is not there, this interelectronic term, if it is not there, then we can write this equation. If square by 4 pi epsilon 0 r12 is neglected, then the Hamiltonian become H1 is minus H cross square by 2me del 1 square. We can write the potential part 4 pi epsilon 0 r1 minus H cross square by 2me del 2 square minus 2 square 4 pi epsilon 0 r2. So basically this is the hydrogen atom Hamiltonian. So this is the hydrogenic atom like Hamiltonian for electron 1, this is for electron 2. So we can separately write this H1 operator plus H2 operator. So if the interelectronic repulsion term is not there, then the Hamiltonian of the helium atom system can be written as a separate 2 electron Hamiltonian. Now, what is the problem then? The problem is that if we take this approximation, that means square by 4 pi epsilon 0 r12, if it is neglected, then what is the outcome of the energy of helium system? So if Hamiltonian can be separated by two separate electronic Hamiltonian, the total energy will appear as E1 plus E2. If you remember that the energy of one electron system, but here is the nuclear charge is plus 2 electron, not 1 electron as in hydrogen atom. So that will be 4 into minus 13.6 electron volt plus 4 into minus 13.6 electron volt. In total, it will give a value of minus 108.8 electron volt. So this is the theoretical estimate of the energy value of helium atom system if the interelectronic term is neglected. But what is the experimental value? The experimental value is minus 79.0 electron volt. So the experimental value is nowhere near to the estimated value. There is already almost 40% of error. 40% of error. So it clearly shows that the interelectronic term cannot be neglected. So you cannot neglect these terms. You have to take this term in your Hamiltonian, then try to solve the problem. So that's why two electron system is not exactly solvable. So we have to resort to some approximated method by which one can calculate the energy for the multi-electron system.